Um, there just really aren't that many, because I think Suncheck is kind of only just sort of gaining popularity. But so you have like Jolt, the Irreducible folks from Irreducible who came up with Binius. They have a Binius repo which has benchmarks for Ketchak. And we'll can compare that to like Plonky 3, which is based on univariate. This is based on Starks and Fry. Binius is based on Sumcheck, and the Binius commitment scheme. And then you have Polyhedra, which is like fully based on the GKR protocol. And they also have some benchmarks for Ketchak as well. And I think this is basically all of your Sumcheck based benchmarks today. I'm sure there are more, but these are maybe the three of the more prominent ones. And all of these are sort of through. Well, Polyhedra might be doing some conversion in the end between multilinear and univariate. I'm not sure. Jolt and Binius are multilinear all the way through, so there's no sort of converting in between univariate and multilinear. It's pure multilinear. So that's just the benchmark situation today, but I think it's going to get a lot better as Suncheck winds up getting incorporated into more protocols, and some of the protocols do use Fry or potentially some other univariate commitment schemes. So we'll get more information about how these all perform in comparison to each other in the coming months. Hopefully that's somewhat helpful. Okay.
Hello.
Yeah. Hi. Another question?
Yes. If I remember correctly from the last session, you mentioned that algebraic hash functions would be somewhat close to the normal hash functions, the binary hash functions that we are used to. Could you elaborate on that? And also, like, I could see that there are some papers about something called monolith hash, that they are in order of like few constraints. It's unbelievable. So could you also elaborate on the upcoming optimizations in hash functions?
Yeah, I can say a little bit. I haven't looked at monolith carefully, but it's it's another paper, a very recent one, as people try to further improve these snark friendly hashes. So this stuff needs to be heavily investigated still, and careful comparisons are yet to be done. So everything I'm going to say is somewhat speculative. But okay, let me see what I want to say here. So on the fly, okay, so firstly, I think constraint counts, I want to clarify, like people, you see this, all the time, like people ask, in order to try to understand how complicated a statement is to prove, they'll ask, how many constraints does it take to represent? Okay, now, this is going to be like way too crude a measure of complexity moving forward. And in particular, well, this will become clearer. I'm literally uploading like a note to ePrint maybe today. With something like Binius, okay, especially like applied to Boolean circuits, which is sort of what you want to implement something like Ketchak or SHA or any of these standard hash functions. Okay, you might you can take you can like pack up to 128 constraints about 1-bit values into a single constraint about 128 about a GF2 to the 128 field element. Okay. And so, it's not going to be enough to say how many constraints are there. You're going to have to talk about like which subfield is the constraint over, because one constraint over the whole field might be powerful enough to capture 128 constraints over like, Boolean values, which are exactly the values that arise when you're proving things about standard hash functions. Okay. And so, I don't know. I looked at nothing from Monolith other than the abstract so far. But if you have three constraints over Goldilocks, I don't even know what field Monolith uses, right? But three constraints over Goldilocks could well be, more expensive to prove than 128 constraints over GF2. And then that's the question, vis-a-vis, like how expensive is it to prove you did one of these hash evaluations correctly? And then the other question is, well, forget about proving you did it correctly. How fast is it to just do the hash? And there, I don't know what the answer is offhand, like Monolith versus Ketchak. But my guess is that, if Monolith is faster than Ketchak, it's not by much. And eventually in the long future, there will be, widespread hardware support for something like Ketchak. Today there isn't, but, since Ketchak is related to the NIST standard SHA-3, eventually there will be. And once that's the case, there'll be major benefits to using Ketchak because the hardware will be there to just make it really fast, if you're ignoring proving. So that's about the best I can say right now. In terms of like how fast like Binius's snark for Ketchak will be, I can just give it, an update on that because I just checked in on those benchmarks most recently. So as of today, like Binius's, like snark for proving Ketchaks is, it was going back and forth with Plonky 3, where, Binius was 2x faster, and then Plonky 3 was 2x faster. Now I think Binius, as of like a week ago, was 3x faster again. But more than that, like it pushes, like whereas Plonky 3 has a lot of prover work in the commitment scheme, with Binius, like essentially all of the prover work is in Sumcheck. Okay, um, uh, and the Binius Sumcheck implementation does not yet, so not yet any optimizations, capturing the fact that Sumcheck is being applied over small characteristic fields, particularly the characteristic 2. So this technique of like, well, I don't know if they might be doing constraint packing, but, so I want to be very hand wavy here, but, I expect that there could be yet another order of magnitude or more speed up coming once the Sumcheck prover gets optimized in this implementation. So those are the data points I have now, like in my head. And, I don't know how to compare, Plonky 3's Ketchak proving to, Monolith's prover. I don't know if anyone's done that comparison yet. And if they have, I just haven't seen it. I don't have it in my head. So I can't be more concrete than what I've just given you. Yeah, let me stop rambling there. But there's a lot still to play out here. But I'm very optimistic about what I'm seeing with the Sumcheck stuff and standard hash functions like Ketchak. It already is looking pretty nice. With this 3x speed up thing. And there's just clearly a lot more juice on the table for optimizations there. Hopefully that was somewhat helpful.
Thank you.
Yeah, thanks for the question. Okay. All right. Well, as is typical, for 40 minutes in, we're getting to the new content, but hopefully the questions are valuable. And let's get to some new content. So yeah, so this is chapter 2 of the book, and I mean, I'm probably just going to cover fingerprinting today rather than not free vods. We'll see how long it takes. And so this fingerprinting technique, actually, it's common. It comes up frequently in snarks, but what we're going to discuss today is not a snark. There will be no prover. So today there will be no prover. Forget about provers. Okay, what we're going to discuss is just an efficient randomized algorithm for a certain problem. Okay, and basically, why this randomized algorithm will come up in snarks, for what I call the equality problem. in snarks, the prover will often commit to two vectors and typically would not claim they're equal, because if they were equal, it shouldn't actually need to commit to both of them. Like, why commit to the same thing twice? You can just commit to it once, and the verifier can, if it wants to treat it as two separate commitments, that's sort of silly. But often in snarks, this is very, very common. You'll see what's called a permutation argument, and that's saying that two vectors are permutations of each other. And so fingerprinting is very, very closely related to permutation checking. And so what will often happen, so let me say related to permutation arguments, what will often happen is the snark prover will commit to two vectors, will claim that those two vectors are permutations of each other. And the way it will prove that they're permutations of each other is it will prove it correctly ran this fingerprinting-based randomized algorithm. Okay, and I will actually, since I'm not going to cover free vaults today, I guess I will cover this today. It's not in the book, or at least not in chapter 2 of the book, but I will cover the permutation argument today. But we're going to start with equality. Okay.
Excuse me, can I ask a small question just on the fly? Is this permutation argument for wires, or is it used in another space of the snark?
Yeah, great question. So the term permutation argument in snark design is sort of unfortunately overloaded, and I think in Planck, to capture the wires of the circuit, they say that it's often called a permutation argument, but there, I think it's really what I would call like a known permutation argument. So it's like, when I say permutation argument, I mean that you have two vectors A and B, and B is some permutation of A, and I don't care what the permutation is. So that is, the entries of B are the same as the entries of A up to reordering. Okay, but like a known or a fixed permutation argument is like known permutation argument would be, like someone has committed to some specific permutation sigma. Someone honest in pre-processing has somehow committed to sigma, is a committed permutation. And the claim is that B is sigma of A. Okay, and that is often that I think something like Planck really wants a known permutation argument, whereas the sum check based snarks that I personally work on and have kind of clearest in my head, I've never seen known permutation arguments needing to come up. Some permutation is enough. So I will cover today some permutation, which I think it's much simpler than a known permutation argument. Like, known permutation argument is just is more complicated to deal with, because someone's got to commit to sigma. You got to tell me exactly how sigma is sort of specified, and it's just clear. It's a more specific statement to prove that bi equals sigma of what is it? Sorry, bi equals a of sigma of I for all I. It's just a more complicated statement to prove. Does that answer the question?
Thanks a lot. Sorry for interrupting in the middle.
Yeah, no, I think the questions are important, so please.
Professor, just one. So you said that the permutation can be that of the wire. So this is what probably baffles me a lot. So if the wire vector is permuted, then the polynomial that the circuit is computing won't be the same. So what would be the motivation for permuting the wires?
Yes, well, let me just come back to the sample polynomial IOP I gave last time and then sketched again today. So, the constraint capturing like correct operation of gate I, was that the value assigned to gate I is the product of the values assigned to the first in-neighbor of I and the second in-neighbor of I. Okay, and so, this is not necessarily a permutation, but the way I'm describing it, but it's going to give you a sense of, why a known permutation would come up, right? So Imagine that every gate had what would make this a permutation. So imagine one of I were a permutation. And I think if you bring in like what are called copy constraints, you can make this happen. I don't have Planck fully in my main memory, so I don't want to say anything wrong about Planck. But so just imagine in one of I were a permutation of the gates. So every gate was the in neighbor of exactly one other gate. And similarly, in two of I were a permutation of the gate. So every gate were the second in neighbor of exactly one other gate. Right. Then, the verifier in this snark needs to evaluate, winds up needing to evaluate like G at a random point, G composed with in one at a random point, and G composed with in two at a random point. Okay. And so if in one is a permutation, a specific permutation, and in two is a specific permutation, then, that's I'm waving my hands. That's where permutation arguments are going to come in. Like, someone honest is going to commit to in one and in two in pre-processing. The verifier is just going to get that commitment, and essentially that specifies the circuit as far as the verifier is concerned. That's like that's capturing the wires of the circuit. And out of those two committed permutations, the verifier is going to be able to obtain in one evaluated at R and in two evaluated at R. And then from those evaluations, it's going to be able to obtain from the commitment to G, G at in one of R and G at in two of R. So that's, again, waving my hands. What I just said is not precisely a permutation argument, but that's why permutations come up. Does that help a little bit?
At least I understood where it's to be applied. I'm not sure why.
Yeah. Yeah, let's revisit this, later, when we actually cover details of these univariate polynomial based snarks, right? Like I guess like this, G composed with in one is quadratic degree, so this is not a practical snark no matter what, which is why there's not a direct correspondence between what I've written on the iPad here and things people actually use like Planck or whatever.
Okay, sure, sir.
We can't hear you, Justin.
Yep. Can you hear me now?
Yes.
Okay. Sorry about that. I guess the phone call, let me put my phone on. I thought it was on Do Not Disturb, but the call came in and somehow that muted me. All right. And back to share screen. Okay. Can you see my screen?
Yeah.
Yeah. Yes.
You can. Okay, great. All right. Sorry about that. Okay. So here's the setup for the equality problem. So let's say we have two entities, Alice and Bob, and say Alice has a length n vector x, and Bob has a length n vector y. And say the entries of these vectors are elements of some field. And if you don't know what a field is, since I'm running behind today, I'll define a field next time. But like, just think of a field as like think of it as like the rational numbers or something. So they're just numbers. You can add, subtract, multiply, and divide them, and let's just leave it at that. Okay. Yeah, and what Alice and Bob want to do is determine, are they the same vector? Okay. And say Alice knows x, but Bob does not know x. Bob knows y, but Alice does not know y. And all they want to know is, are they the same vector? You know, that's the answer is yes or no. Okay. Now it turns out, okay, and their goal, I'm framing this as what's called a communication problem, which means they, you know, Alice can send some messages to Bob, and Bob can reply, and Alice can, you know, reply to that, and so forth. And they want to, you know, determine what the right answer is. You know, does X equal Y or not? Exchanging as little information as possible. Okay. And so like the trivial solution would just be for Alice to send her whole vector X to Bob, and for Bob to just check entry by entry, you know, does X equal Y? Now he knows every entry of X, so he can check this and output yes or no. Okay, and so that the communication cost of that is like n field elements, right? That's like the completely trivial solution. Now it turns out if they want to know the right answer with certainty, they actually can't do any better than that. So this is optimal if, you know, if they want the right answer with probability 1. You know, they want to be absolutely certain. Okay. But if they're allowed to sort of make some random decisions and have a very, very small probability of outputting the wrong answer, you can do massively better. And that's the way they can do that is something called fingerprinting. Okay, and so that's what I'm going to cover now. And so in principle, they can, you know, with randomization, and they can make the probability of getting the wrong answer like really, really small, as I'll explain shortly. With randomization, this communication can come down to, so the communication, COM, short for communication, can be just, I guess it would be 2 field elements, something like that. So you go from n field elements all the way down to 2. You know, so like, you know, if these files have gigabytes of data in them, or, you know, terabytes, you know, you go from Alice sending a terabyte size file to Bob down to her just sending, you know, 256-bit field elements or something. It's like, you know, night and day in terms of how much data gets sent from Alice to Bob. All right, and so here's how the protocol works. So Alice interprets her input X as the let's say the coefficients of a polynomial, say a univariate polynomial of degree n-1, right? So that is, you know, let's say X is, you know, interpreted as a polynomial P is Z, you know, which is the sum from I equals 0 to n-1 of X sub I times Z to the I. Yeah, and what out, you know, similarly, Bob interprets his input Y as the coefficients of a univariate polynomial Q. Q is Z is sum from I equals 0 to n-1 of Y sub I times Z to the I. Okay, and what Alice will do is we'll pick a field element R at random. So she just picks a random field element, and she sends to Bob R and P of R. Okay, and Bob will output equal if P of R equals Q of R, right? Remember, Bob knows Q, but he doesn't know P, but Alice just told him one evaluation of P of R. So Bob can compute Q of R on his own, and Alice just told him R and P of R. So he can check whether this quality is true, and otherwise Bob will output not equal. Okay, that's the whole protocol where Alice just sent 2 field elements to Bob. Okay, and the claim is that, you know, this protocol outputs the right answer with overwhelming probability. So, and specifically, if X and Y are the same, then Alice and Bob always outputs equal. You know, so he outputs equal regardless of the choice of R. And that's just because if P and Q are the same polynomial and you evaluate them both at the same point, of course they spit out the same evaluation. So that claim is obvious. And then the interesting direction, although it's extremely simple, is if x does not equal y, if they're not the same vector, then the probability that Bob outputs the wrong answer, so the probability that he outputs not equal, even though he should output not equal, is at most the degree of these polynomials, which is like n-1 or something, over the size of the field. So, think of this field of a size like 2 to the 256 or something, and n as, I don't know, these vectors have length, I don't know, maybe even if they have length a trillion, that terabytes of data, this would, this probability would be still less than like, 2 to the minus 200 or something like that, which is, that's cryptographically small. That's actually a lower failure probability than all sorts of deployed snarks today. So, basically, like, never in the history of the universe will they ever make a mistake. Like, it's possible if they get really, really unlucky, if x does not equal y, there's, a very small number of values of r that would cause them to output the wrong answer. But, if the field is this big, the probability they actually wind up picking one of those values of r is, it's more likely that, like, your computer gets hit by an ion from the cosmic background radiation that causes it to make a mistake or something like that. And this is to see that this is true, that this claim, the second bullet, is true. It just follows from the fact that if x does not equal y, then q and p are different polynomials, but they both have degree n-1. So they're different polynomials. They both have, degree at most n-1. And so there's just like a fact that you maybe saw in, even middle school or high school math. I think it's the fundamental theorem of algebra or something like that, two different, univariate polynomials of degree d agree at most, what I always have to go to, I'm always off by one unless I think about it. Like, so two lines, that's degree 1, and they can agree on at most 1 point. So they agree at most d points. Right. And, another way of saying this is equivalent to the fact that any degree d polynomial that's not 0 has at most d roots. But I think this is so this is equivalent. These are the same statement, just in different forms. And I think this is what people call the fundamental theorem of algebra, or maybe the first fundamental theorem of algebra or something. I don't. It's been too long since 8th grade math or whatever. And to see that they're equivalent, just note that if you have two different polynomials p and q, both of degree at most d, then their difference p minus q is not the 0 polynomial. Okay, and any root of p minus q is an agreement point of p and q. So the fact that p minus q has at most d roots is equivalent to p and q agreeing on at most d points. So that's why these two facts are equivalent. And so, to come back to this claim here, the second bullet point, if x and y are not the same vector, then p and q are not the same polynomial. But Alice and Bob evaluate the p and q at a randomly chosen point r. There can be at most n-1 points r at which they agree, because they both have degree d-1, but r is chosen at random from the whole field. So the probability that r chosen at random from the whole field is one of the at most n-1 agreement points is at most n-1 over the size of the field. Okay, so that's fingerprinting as a technique for checking equality, right? And again, it's a very efficient procedure, at least as determined by communication cost. Because if you didn't allow any probability of failure at all, if you wanted this probability to be 0 instead of 2 to the minus 200, you would need Alice to send all of her vector to Bob. But as long, with failure probability 2 to the minus 200, Alice only has to send 2 field elements to Bob. That's equivalent to like 2 entries of her vector. So just an enormous savings. So that's fingerprinting for equality. And I'm now going to do fingerprinting for permutation checking, but I'm going to, before I do that.
Hi, Professor. What is considered to be cryptographically small but secure enough for these protocols?
Yeah, great question. So my personal answer would be 2 to the minus 128 or smaller. But many people in the community seem totally fine with 2 to the minus 100 or smaller. The deal is, I can do a more detailed discussion about this, I guess, some other time. But the deal is, in the SNARK context, these probabilities will roughly translate to the amount of work an attacker would have to do, the inverse of the amount of work an attacker would have to do to find a convincing proof of a false statement. And so, like 2 to the 80, like operations is actually feasible today. It's very expensive, but it's feasible. I think the Bitcoin network does 2 to the 80 like SHA evaluations like every 30 minutes as of 2 years ago. It probably does even more now or something, right? So people can do 2 to the 80 operations today, given enough computer hardware or whatever. And so you definitely want the probability to be smaller than 2 to the minus 80, because when you turn everything into a SNARK, a 2 to the minus 80, like, attack probability, or, would turn into, 2 to the 80 computational steps required to complete an attack successfully. So 2 to the minus 100 is beyond today's, computers. Like, I think even nation state actors probably can't muster 2 to the 100 like hash evaluations or something like that. But it really doesn't leave too much buffer room for better attacks, right? So when people say that the security level or the of a SNARK is 2 to the minus 100, typically what they mean today is there's a known attack that will achieve success probability like 2 to the minus 100, and it's possible in the future we discover better attacks. And so that's why I advocate for 2 to the minus 128, is so if slightly better attacks are known, maybe that improves the success probability a little bit, but it'll still be better than 2 to the minus 100. So it's like 2 to the minus 100 is okay if like really like the best known attack is the best possible attack, but it doesn't leave much, if you, yeah. So I'll stop rambling. That's my answer.
Okay, thank you.
Mm-hmm. Other questions? Okay. And by the way, the answer to your question can differ by context. There are different notions of, like, if there are different notions of security, depending on whether you run a protocol like interactively versus non-interactively. Of course, any SNARK, the N means non-interactive, and so my discussion here just was applicable to the non-interactive setting. In interactive settings, for reasons I won't get into now, it can be much more reasonable to have attack success probabilities better than 2 to the minus 100. We don't have to get into that now, but yeah. So cryptographically small, think like numbers like this: 2 to the minus 128 or 2 to the minus 100. Okay. Other questions?
Thank you.
Great. Okay, let's talk about fingerprinting for permutation checking. And I think that's all I'm going to wind up covering today. I think that's actually a pretty good, even though it was, most of our time was spent on recapping questions. I actually think this is pretty good content for one session. Okay, so now let's say, Alice and Bob still have their vectors X and Y, but now they want to know, is Y a permutation of X? Okay, so another way of saying that is, is Y the same as X up to reordering? So it has the same entries, but is like, just a different ordering of those entries. Okay, and here, I think, by the way, I think this is an exercise in the book, so I am giving away the solution to an exercise, but that's okay. I think it's an exercise. It's been a while since I looked at them. So Alice is going to interpret X as a degree n minus 1 polynomial again. Maybe it's degree n now. I'd have to think about it. So Alice interprets X again as a degree n or n minus 1 polynomial, univariate polynomial, but in a different way. So now, rather than interpreting the entries of X as the coefficients of the polynomial, instead they'll be interpreted as the roots of the polynomial. So now P of Z will be the product over the entries of X of Z minus Xi, right? So this is the polynomial that, has as its roots, like, it maps every entry Xi of X to 0. And if the number 3 appears, 8 times in X, then, 3 is a 0 of multiplicity 8 in P. And similarly, Bob interprets Q or his vector Y as a polynomial Q, but now the entries of Y are the roots of this polynomial. Okay, and other than the different, the polynomials being different than before, the protocol is the same. So Alice is just going to pick a random R from the field, and she's going to send to Bob R and P of R. And, Bob is just going to check, like, does P of R equal Q of R? And if so, he'll output, yes, they are permutations. So he'll output yes, they are permutations of each other. And otherwise, he'll output no, they are not permutations of each other. Okay. And, the analysis is basically the same as before, but let me just explain it. So, if X and Y are permutations of each other, or, Bob outputs yes, no matter what, regardless of what the choice of R is. And if they're not permutations of each other, then the probability Bob outputs yes is at most the degree of P and Q, which I guess is degree n now, rather than n minus 1, I think. Anyway, it's at most n over size of the field, which again, if the field is like a 256-bit field, would again be, in practice at most 2 to the minus 200, which is definitely cryptographically small. Yeah, again, so what's going on is, if X and Y are permutations of each other, then, the things being producted together, Z minus Xi and Z minus Yi, it's the same set of factors, right? And multiplication, what is it? Is it commutes? Like if you Z minus 1 times Z minus 2 is the same as Z minus 2 times Z minus 1, right? It doesn't, multiplying these Z minus Xi's together, like, just doesn't care what order X comes in. It's sort of interpreting X in an order independent way. It only cares about, like X as a, like, kind of as a set, as a multi-set. And so if X and Y are permutations of each other, P and Q are the same polynomial. And if X and Y are not permutations of each other, they're different polynomials because, they have different roots. If you pay attention to multiplicities, they have different roots, so they can't be the same polynomial. So again, the analysis is the same. If they're the same, if they're permutations of each other, P and Q are the same polynomial. You evaluate them both at the same point. Of course, they're going to equal at that point because they equal everywhere. If they're not permutations of each other, P and Q are different polynomials. They're both of degree n. So the probability over a random input that they agree at that input is at most n over field size. And this, as simple as it is, this is actually like really, really key to some state-of-the-art snarks. So this comes up in lookup arguments all over the place. It also comes up in things like Planck. Planck uses like a known, we discussed this before, known permutation argument, but known permutation argument is of course somehow related to unknown permutation arguments, which is exactly what this is. And just to repeat or recap, what will happen in snarks is the snark prover will commit to these two vectors X and Y. okay, it will then, the random point R will be chosen via fiat shamir. So that what's important is that the prover commits to X and Y and only then learns the random point R. And then it will prove that it correctly ran this permutation checking procedure on the committed vectors X and Y. So that is, it will prove that it correctly computed, let me just plug in R for Z. The snark prover will prove that it correctly computed these two giant products. Okay, and that the way it proves that is what's called a grand product argument. And there are, several grand product arguments in the literature. But that's how the these snarks actually work is, the prover commits to X and Y. After it commits to them, it then learns what R is via fiat shamir. And then once it learns what R is, it's able to prove that it actually ran this permutation checking procedure. And that permutation checking procedure just amounts to computing two grand products and seeing if they output the same thing. Okay, so yeah, that's what I wanted to cover today. And hopefully you see, while it's very simple, you see like the remarkable power of two things. Like there's sort of two important things going on here. So one important thing is the power of interpreting vectors as, polynomials, where if they're univariate, as was the case today, the degree of the polynomial that you interpret the vector as would typically be like the length of the vector. And then like evaluating the polynomial at a random point, polynomials at a random point. And so what's going on is like global properties of different vectors can be checked by evaluating the associated polynomials at like a single point, like whether X and Y are equal or permutations of each other. That is a property involving every single entry of X and Y. Nonetheless, I can check it by evaluating their associated polynomials at just one point. Of course, that one evaluation has to be from like the entire field, rather than while the vectors themselves might refer only to like, n different evaluations of them. Anyway, so I'll give a, next time I'll give a perspective on this from what's called the point of view of error correcting codes. So I'll explain that. I'll leave that as just a tease for next time. But yeah, so the power here is coming from treating vectors as polynomials. Somehow the polynomials have certain like distance amplification properties. That's getting into the error correcting code terminology. So that any two vectors that kind of differ at even a single location, the associated polynomials wind up differing almost everywhere because they're not the same polynomial, but they have degree at most n, and so they can agree at most n points. But you wind up evaluating them at a random point from a giant field which has size much bigger than n. And so you're seeing also the power of randomness. So if you wanted literally zero probability of making a mistake, Alice would have to send her whole vector to Bob. But if you allow a cryptographically small probability of making a mistake, all of a sudden Alice only has to send like two entries, of two field elements to Bob. Okay, so that's fingerprinting. And again, I told you how this will be useful when there's a prover. But fingerprinting as a technique in its own right, like there is no prover, right? Like, there was no prover here. Just Alice had X, Bob had Y. They wanted to ascertain whether X and Y together satisfied some property. And ultimately what they did, there was no prover, just Alice picked a random point R and like evaluated a polynomial associated to X at R and like sent it to that evaluation to Bob. That was it, no prover. So next time we're going to discuss Friedwald's algorithm. That will be our first full protocol with the prover. And from there, we'll quickly move to the sum check protocol and see some really nice interactive proofs. Okay, so that's everything for today. If anyone wants to ask any more questions, I can stick around for a little bit. And otherwise, thanks for bearing with me through all the ramblings as always, and I'll see you next week.
Is there any particular reason, Professor, for this community to call it fingerprinting and rather than just sword zipper?
Well, yeah. So two things. The term fingerprinting. So arguably, I am introducing that term to, possibly, right? So it comes from the randomized algorithm community, and I'm trying to think. I don't remember how the how the snark community referred to the technique, over time. Um, Certainly, like permutation checking has just been called like permutation arguments, and often attributed to Planck itself, when this technique that I just described to you today dates much back many decades in the randomized algorithms literature. Now, as for short zipple, so when you're dealing with univariate polynomials, like short zipple is kind of overkill. This property that any 2-degree D univariate polynomials agree at most D points or whatever, that's really like the fundamental theorem of algebra. Where short zipple gets, so like short zipple for univariate polynomials is actually the fundamental theorem of algebra, and like not attributable to Schwarz and Zippel de Milo-Lipton, which was results from, I don't know, the 80s or something. Where short zipple gets meaningful, and not just the fundamental theorem of algebra, is when you talk about low degree multivariate polynomials, and that's where short zipple becomes something more powerful than the fundamental theorem of algebra. So yeah, anyway, I'd say the terminology from fingerprinting is more historic, from the randomized algorithms literature, and also, I guess, a little bit intuitive, right? Like, you think of a fingerprint as like an almost unique identifier for a person, right? Like, so there are some people whose fingerprints are similar enough that if you take both their fingerprints, maybe like today's fingerprinting machines would say they're the same fingerprints when they're not. And so that's sort of capturing what's going on in this protocol, where if you fingerprint me, Justin, twice, it's gonna say like those are the same fingerprint with certainty. But if you fingerprint me and some other person in the world, the probability that our fingerprints match is almost zero, but not literally zero, right? And so I think the term fingerprinting is just also like a little more intuitive than author names, I guess. So that would be the other reason to call it fingerprinting.
Thank you, sir.
Could you, if possible, briefly touch upon the pooling set method that is mentioned in the book?
Sorry, what method?
The pooling set method in communication
Oh,
complexity.
okay. Yeah, so the fulling set method is just a way to show, sorry for, I made this assertion that if Alice and Bob want to output the right answer with probability 1, they can't do better than Alice just sending her whole input to Bob. Okay, and that's actually, it's pretty easy to show that if you insist that Alice send one message to Bob and that's it. It's like, intuitively, if she leaves out even like one entry of X, then potentially X and Y agree everywhere but that entry. And then, but since she didn't send that final entry, they don't actually know if they agree at that entry. So how can you be absolutely certain, that they're the same vector? It's possible that they disagree at just one entry, and that's the entry Alice left out. Now, that's an intuitive argument. It actually is, a little harder to prove what I just said than the intuition I just gave. But what is more complicated to show is that, like, let's say you're willing for like Alice to send, 10 bits to Bob, and then Bob to reply with, 3 bits, and then Alice to reply with 10 more bits, and Bob to reply, and then Alice, so you have this like interactive thing. And it turns out that Alice, like the total communication here still has to be end field elements, right? Like, so just to give another example that is no cheaper than the simple Alice sends all of X to Bob, but is different, right? Like Alice could send X1 to Bob, Bob could send Y2 to Alice, Alice could send X3 to Bob, and eventually they wind up, Alice sends half of X to Bob and Bob sends half of Y to Alice, and then they're able to tell, entry by entry, are the two vectors equal? And like, so that's different. It's a different protocol than just having Alice send all of her entries to Bob, but it has the same cost in the end. It's still, in total, one entire vector was transmitted, somewhere in one direction or another. And so, if you want to prove that even interactive protocols that never make a mistake require end field elements to be communicated, you can do that with something called the fooling set method. Okay, but I don't want to go into more details than that. That's just like, that's the, if you were to, think really hard and like write, if you never saw what's called communication complexity before, this is like covered in like chapter 2 or 3 of the book on communication complexity. Like it took like, some very smart person to figure out like, the way you rule out like any interesting, protocols, even when there's interaction between them, is it's just the analysis technique that rules that out. So mentioning the fooling set method was just really an aside. It's not going to come up again in this study group. Was that sufficiently detailed?
Yeah, thank you. It gives me a direction to go to if I need to.
Yeah, and I can also tell, so I'm working on a paper that will try to use communication lower bounds to give evidence that certain popular snarks today are optimal. And so that it's going to take a couple months for that to be ready, but I can flag that in the Discord chat. And that will talk a lot more about communication lower bound techniques. And like, to be clear, like this is not like a connections between communication complexity as I'm discussing here and snarks. It's not like a standard thing. This is, I just happen to work on the two areas, and as a result, like see them as like very, very closely connected. But they're, I think most like snark courses will never utter the words communication complexity in the sense we're talking about today. So just, just flagging that, but I think they are actually closely connected, and the connections will hopefully become clearer soon. All right.
Thank you. Is your paper attempting to standardize something along those lines?
No, it's I'm trying to prove things like all right, let me try to, I'll say a few sentences about it. Okay, so like bulletproofs as a polynomial commitment scheme. So this was one of the, I discussed in my first session here, like 3 classes of polynomial commitment schemes, and bulletproofs was like the most popular scheme from one of the 3 classes. Like it's transparent, and it uses groups, right? And like it's got nice short proofs, but the verifier is slow. Okay, so I want to give evidence, and then there's there's something called Dory, which is a lot like bulletproofs, but the verifier is fast. Okay, but unlike bulletproofs, Dory uses pairings. Okay, so I actually think you can use communication complexity to give very strong evidence that you need pairings if you want to get take bulletproofs and make its verifier logarithmic time, right? And there have been several efforts actually to do that without pairings, and they've all broken. They've all been wrong. And I think it's not just that those efforts had a bug in them. I think like really there's no way to do it without pairings, and you can use communication complexity to at least give strong evidence for that. Like another thing I want to show is there are certain costs in like the lasso lookup argument, where if you have a lookup table size n, there are certain costs in lasso that grow like c times n to the 1 over c, for a parameter c. Okay, and I think that this is inherent. Like any lookup argument needs to have costs that grow like this, and so I think you can use communication complexity to give evidence for that as well. So those are the sorts of results I'm working on, and like no one has actually really connected, as far as I'm aware, statements from snark land like I just made to communication complexity before. But I think you can, like, basically, I think, like, how snarks, people do understand, that snarks can be basically separated into two components, like a polynomial IOP, which people will call that the information theoretic component. There's no cryptography, is what that means. And then the commitment scheme, the polynomial commitment scheme, which they'll call the cryptographic component. Okay. But what I think is going on roughly is that the commitment schemes themselves also can often be split into two components, an information theoretic component and a cryptographic component. And again, like, this is somewhat known. I don't want to take too much credit for this, but I also think it's, like, somewhat underexplored. And I think a very good way to formalize the information theoretic component is actually communication complexity, right? So in this setting that we discussed today, where there's, like, Alice and Bob, and they want to compute some function of their joint inputs, there's with minimizing communication between each other, there is no there's no cryptography, right? So it's a wonderful model to capture. It's an information theoretic model. There's no cryptography, and because it's an information theoretic model, you can prove unconditional lower bound, right? So you can prove, like, unequivocally, there is no communication protocol with fewer than n bits of communication between them, if they want to output the right answer with certainty, right? You can prove things like that, which as soon as there's cryptography around, everything becomes conditional, right? Like, if discrete log is intractable, then the snark is secure. You get those conditional statements like that. And so I think that communication complexity is sort of a really nice way to formalize and identify the information theoretic components inside commitment schemes and other snarks. And we can, and then because we can actually prove unconditional communication lower bounds, you can interpret that as evidence, that certain commitment schemes are optimal. And it's only evidence because right, what you're showing is, like, the information theoretic component is optimal, but, like, maybe we invent better cryptography, and so, like, you can start with you can get rid of the information theoretic component, or, like, have a different information theoretic component. And so just showing optimality, that the current information theoretic component is optimal, as an information theoretic object, doesn't literally tell you that the commitment scheme itself is optimal. But I think it can give very strong evidence that the commitment schemes are optimal. Basically, you'd have to deviate majorly from the current way of designing them to do any better, is sort of the way to interpret this kind of result. Was that helpful or interesting?
Sounds very interesting and fundamental. I hope you succeed. Best of luck.
I appreciate that. Yeah, hopefully I'm not making
Professor,
any
a quick question.
yeah, go ahead. Yeah.
A quick question about that. So when you say optimality, you're talking about that the communication complexity is logarithmic in the circuit size. Is that the way to put it?
Well, it depends, I guess. So basically, like, what the bulletproof verifier, if you're committing to or dealing with a polynomial of size n, the bulletproof verifier runtime is linear in n. It's actually worse than linear, but let's just call it linear in n. And so where is that coming from? Like, there is you can define. This is what the paper will explain, right? Hopefully,
No, so
you can.
in this notation, n is the circuit size, right?
Yeah, I mean, here I'm thinking of bulletproofs as a way to commit to a polynomial, but in snarks, the size of that polynomial is typically about the size of the circuit you're dealing with. So sure, think of n as circuit size if you'd like. And the bulletproof verifier, runtime is n. And when you translate bulletproofs into a communication protocol, like, you get rid of all the cryptography and say, this is, like, the communication protocol, that bulletproofs is, after you add cryptography to the communication protocol, again, very vague statements I'm making. That's what the paper is going to formalize, hopefully. this linear in n runtime of the bulletproof verifier corresponds to some like linear communication in the communication setting, right? So I don't want to give away too many details or I'll like get myself scooped or something, but like, it's like roughly, there's there's Alice and Bob, who somehow have two inputs. I'm not telling you, like what function they really want to compute of those inputs that captures bulletproofs, but roughly speaking, there's a way to say, hey, unless Alice and Bob, have some power that, ultimately we only know how to convey to Alice and Bob, if cryptographically with pairings, Alice actually has to send n bits to Bob. They can't do better than that. And so the linear runtime of the bulletproof verifier winds up turning into high communication complexity, if you sort of get rid of the cryptographic component of bulletproofs and just distill an information theoretic analog of it to get, it's not obvious what I even mean by that. But then the linear runtime of the bulletproof verifier kind of translates into linear communication of the communication protocol.
So the optimality is just trying to confirm that this is the correct way to put it, is that the optimality is about that the communication complexity is going to be linear in the circuit size.
Yes, yeah. So so to put it another way, I guess what I'm trying to do is identify a communication model, meaning there's Alice and Bob, and maybe there's a Charlie or a Merlin in there or whatever, and there's some problem they want to solve. Alice knows some input X, Bob knows some input Y, and bulletproofs, like at its core, when you strip away the cryptography, gives some protocol in that model. Okay. And that protocol has like Alice sending n bits to Bob somewhere, and and the hope is that we can show that there's no way to do better than that. And if we show that, then that is sort of evidence that the bulletproof verifier really needs linear time. Now that there's a leap, right? Because bulletproofs involves cryptography, and this is just a communication protocol, right? There's no cryptography in it. So like proving Alice has to send n bits to Bob in the communication setting doesn't really mean bulletproofs as a polynomial commitment scheme needs a linear time verifier. But it does mean if you wanted to get rid of the linear time verifier in bulletproofs, somehow you'd have to majorly change the way bulletproofs work, right? Like today, I'm saying like bulletproofs work, like there's a communication protocol in there, and then you get a polynomial commitment scheme by sort of, throwing some cryptography on top of it, so that like Alice and Bob together are implemented by the bulletproof prover or something like that. Yeah, I don't know. I should stop rambling. Hopefully, some of this is going through, but coming up.
Yes. Thank you, sir. But one more question is that you mentioned that it is also a proof of lower bound. Is that not the way to look at it?
Yeah, it is. It is. So, I'm hoping to prove a communication lower bound that says, in the communication problem that bulletproof solves, literally no protocol can have better communication costs than bulletproofs achieves.
I see. Yes, okay, understood. Yeah, thank you, sir.
Great. And so this Fulling set method, which is briefly mentioned in the book, that is an important technique for proving communication lower bounds. Now, this paper I'm working on, and I'm going to be people will probably just forget I ever said this here, but hopefully it works out. It uses even more sophisticated lower bound techniques than the Fulling set method, but the Fulling set method is a very important example of a lower bound technique in communication complexity. So that's why it's mentioned in the book. Is the chapter 2 is meant to convey why randomized algorithms can be much more efficient and powerful than deterministic ones. Deterministic ones meaning you require the right answer to be output with certainty. So I wanted to have some discussion. I assert that any deterministic algorithm for the equality problem requires Alice to send her entire input to Bob. And I didn't just want to assert that and, say absolutely nothing about how one might, actually prove that that's the case, that you can't do better than that trivial protocol if you don't have randomness. So I mentioned the fooling set method, but it's really, not related to snark design, at least not until or unless this paper I'm working on, trying to actually take communication lower bounds and draw implications for snarks works out. All right. Any more questions?
I have a question. Regarding the sorry. Regarding the theorem about the polynomial equality.
Mm-hmm.
Assume that they are both degree D, but is there any case to be made if they have different degree or something like that? I don't know if it makes any sense.
Yeah. Well, so what's critical? All that matters is that they both have degree at most some bound, where the bound is much smaller than the size of the field. Okay. So what's going on is if P and Q, like the key statement is that if P and Q are two polynomials that are not the same, so two distinct, not equal polynomials of degree at most, some bound D, then the probability, if you pick a random point from the field, that they agree at that point is at most the degree over the size of the field. Okay, so it's okay if Q has higher degree than P, as long as they both have degree at most some bound D, where D is much smaller than the field size, so that this probability is cryptographically small or whatever. That's what's important. In fact, if so when I say that like X was interpreted as a polynomial P, whose coefficients are given by the entries of Q, the entries of X. Sorry about that. Like the degree of this polynomial is at most n-1, but if like many of the final entries of X are 0, the degree will actually be much less than n-1. Like that's fine. That actually potentially only makes life nicer, not worse. Yeah. So what's important is that P and Q both have degree at most n-1, and that n-1 is much smaller than the size of the field than the field. Does that make sense?
Oh yes, but like from the point of view of Bob, I don't really see how he knows that X is the polynomial is.
Yeah. So I mean, there's no untrusted prover here. So Alice is going to behave honestly, right? So like and because of the way we define P, for any vector X, P has degree at most n-1. So Alice is Bob trusts that Alice will pick a random R and send to him R comma P of R, and assuming she does that, like P will have degree at most n-1, regardless of what X is. Okay. In snark land, like P and Q will wind up being committed with a polynomial commitment scheme, and the polynomial, and it'll be committed typically by an untrusted prover who you don't trust, right? And so unlike Bob, who can trust Alice to send R comma P of R honestly, in snark land the verifier cannot trust the prover to like provide P of R honestly. So the polynomial commitment scheme is going to address that issue. So the polynomial commitment scheme is going to guarantee the P of R is going to have to come with a proof pi that indeed the value P of R is equal to the committed polynomial at R, and like that committed polynomial has degree at most n-1 or whatever. So yeah, does that
because of the trust? This guy.
Mm-hmm.
Alice is trusted.
Yeah, because that's it. Because Alice is trusted, and for any input X, the polynomial p, as defined here, has degree n plus n minus 1. Yeah.
Thank
Yeah.
you.
Yeah. Sorry. Thanks for the question. I should have highlighted that. Because there's no prover today, there's no distrust anywhere. Alice and Bob are working together to hopefully output the right answer. Yeah.
I have one question related to this question specifically. So the question about, let's say, checking the equality of two vectors.
Mhm.
So we translate the problem to equality of